Hello SGD, Sacred Geometry Decoded. This video will be a redo of a series I did previously. I have some added information to put in there, and so I just put it out as one video. Ancient Architecture, Freemasons, Sacred Geometry, and Pythagorean Theorem before Pythagoras. Before Pythagoras were people using the Pythagorean Theorem. We'll have a look at that now. Some Lost Science of Measuring the Earth by Robin Heath and John Michel, Little Book of Coincidence in the Solar System, John Martineau, and Megalithic Yard by Alexander Thom. So he's just in the general sphere of measuring the Earth, sacred geometry, coincidence, and how architectural coincidence just happens to blend with beautiful harmonies built into natural time in the universe and the solar system itself, but also measurement. So that would be some I'm often asked what's the best book for sacred geometry. I don't know the answer to that. I sort of I was introduced to it really by Secrets in Plain Sight by Scott Onstott, and ever since then I've sort of followed, almost went out of my way not to look at other people's work so that I wouldn't be influenced by them, and sort of went down my own path. And I have looked, but I could honestly say that there is a Bible of sacred geometry apart from Euclid's Elements. But so anyway, we'll be looking at Pythagorean Theorem and ancient architecture long before Pythagoras. So Pythagoras of Samos, very famous Pythagorean Theorem, a squared plus b squared equals c squared. It has to do with right angle triangles. So right angle triangle, a squared plus b squared equals c squared. So this was a huge, so important, giant leap in this understanding. Is just cannot be underestimated in the applications it has to basically everything, mathematics, geometry, and just all the sciences as well. It's just one of those foundation stones of the knowledge we have. When I originally posted the video as a series, I had a comment thread, and he made the point, well, as we'll see, because you'll find it in ancient architecture long before Pythagoras, but they didn't have the proof. And that's a good point. Now, they did not have the proof, but at the same time, there is no existing proof from the time of Pythagoras. The first mathematical proof of Pythagorean Theorem doesn't appear until centuries after Pythagoras. They understood this, but there was no proof of it. So, as we'll see, there is a tendency, anything before the Greeks, among certain historical philosophies, there was no, the Egyptians couldn't have had it, there's no evidence for it. Well, that argument is good, but if it's applied to Pythagoras and the Greeks of the Hellenistic in that period, well, that argument works in that direction as well. So just to head that one off at the pass. But so most historians won't credit anything prior to the Greeks for understanding Pythagorean Theorem. But again, where's the proof of Pythagoras or of his period? So other people, because there's nothing left of Pythagorean writing by Pythagoras himself. Some would argue, did he even exist? But all that aside, the proof does not appear until later. So yeah, what's good for the goose is good for the gander in that sense. So yeah, it's a heresy for instance, to say the builders of Stonehenge and other ancient sites that they understood Pythagorean Theorem. This is a heresy. So same for Karnak in France or for Egypt as well. Pythagorean Theorem just so powerful, so useful in all fields: survey, architecture, engineering, just science, and all the fields in general. And again, the first, so what are called the Pythagorean Triplets. Pythagorean Theorem works on all triangles, but the 3, 4, 5 triangle is the first of the Pythagorean Triplets, in that 3 squared plus 4 squared equals 5 squared. That's because it's an integer, it's a whole number. So that's the first of the Pythagorean Triplets, 3, 4, 5. The next is the 5, 12, 13. A squared plus b squared, 3 squared, 9, plus 4 squared, 16, equals 25, which is 5 squared. So it's the first of the Pythagorean triplets. The second is the 5, 12, 13 triangle. 5 squared plus 12 squared equals 13 squared. So again, officially speaking, they'll put it to time of Pythagoras, but again, the math proof doesn't exist from that time, doesn't appear until later. But in places such as the Parthenon, there are inherent proportions which are in the Parthenon or are in ancient pyramids, and you'll see it in modern architecture by the esotericians and these very interesting people as well. But so this is the Anne Balkans, but we have the 9:4 now, and the 3:2 ratio. Well, 3 squared is 9 and 2 squared is 4. But you also have the 4:3 ratio as well. So 4, 3, and therefore you get your 3, 4, 5 triangle. But Euclid of Alexandria, Euclid's book Elements. Now it's basically the longest printed, most widely printed, maybe not in numbers of prints, but widespread, because it's not just, for instance, the Bible tends to be in Christian countries, Quran will be in Islamic countries, and Buddhist texts will appear in Buddhist countries, but all religions are looking at Euclid. This is why it's, if not by sheer numbers, but by its spread across the world, this is the most distributed, well-known book, and it's the Bible of geometry. And in that sense, I would say, what's the point of sacred geometry without the geometry? For instance, book 1, like essentially the first page, book 1, proposition 1, how to draw an equilateral triangle. For instance, there we see the Vesica Pisces, which has a 3, so it's 1, 2, 3 wide, and 1, 2 high is 3:2 ratio, from which we get the 3, 4, 5 triangle. But proposition 47, Euclid's Elements, has the 3, 4, 5 triangle. Now, whether the original version of the original version of Euclid has been expanded, so exactly who added what and when from the older surviving, that's a discussion. But in right-angled triangles, the square of a side subtending the right angle is equal to the squares of a side containing the right angle. Just another way of saying the square of the two shorter sides will be equal to the square of the longer side in a right-angled triangle. And this is a common image, so 1, 2, 3, 1, 2, 3, 4, and 1, 2, 3, 4, 5. Pythagorean Theorem, the 3, 4, 5 triangle being the first, but this is a very important emblem that we'll see in other places. And older copies of Euclid, and just want to pause a moment. Okay, so this image of Pythagorean Theorem is a very important one. We'll see it in many places historically. It's one of those emblems, signatures that you'll find around. Again, it's a square of 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5. And well, drawing it this way now, maybe you won't, but I noticed, because I was asked this question a long time ago, and so here we have the 3 on the bottom. Okay, so therefore that's 1, 2, 3, 4 wide. Now, because of this square larger, you would think that the distance from here to the edge here is less from this distance to the tip of the C, but it's actually the same. So from that corner, and you create a right angle triangle, that will also be 4 wide, and I'll show you that in a moment. So it's one of it. So there you see the 3, 4, 5 triangle image, and again, one of these Chartres Cathedral includes a picture of Pythagoras, but from Universal Music by Athanasius Kircher. So you have all these astronomical symbols, musical symbols, but again, the alchemical symbol with the 3 cyclops helping for Hephaestus, which is, I sort of covered this earlier, where you find this imagery just embedded across the alchemical masters and the esotericians and geometricians and metrologists of the past. But again, we see the 3, 4, 5 triangle, so where we get a close-up view. And again, this is one of those esoteric symbols. Now it will be one of the badges that, for instance, used by Freemasons. Now, Freemasons emerged from the stone, the guilds working in stone masons, and tilers and these type of people. So that's why in the imagery of Freemasons you'll see, chisels, rulers, squares and compass, but this is one of the important, it has to do with the third degree and the 47th problem of Euclid. Now they haven't, an interesting, because there's another cursor drawing. So these two squares appear to be equal, so it's creating a 45, well, it's creating a building square 45, 45, 90 degrees, and that's appears in one of other Kirsch's illustrations as well, where it's even marked 3, 4, 5. But anyway, the point is that this is an important process in the move up the Freemasons, and so you have a 3, 4, 5 triangle there. Now earlier I mentioned, so here's just an example. Now, whichever way it's turned, so here we have that square of 5 on the bottom, but if the square of 3 or the square of 4 was on the bottom, you'll always find that the distance across is equal. So again, it's even because the square looks bigger, you'd sort of, without the lines there, you'd think that it extends out further, but it's actually the same distance. Doesn't matter which one's on the bottom, because the angles are always going to be a 3, 4, 5 triangle angle if you extend those lines out. So, but back to the point, and we get to that Euclid, and again official history. So it wouldn't be heresy to say that it was used in the Parthenon, for instance, but can we find it much earlier? And we can't mention again the Vesica Pisces 2:3 ratio. So again, when you cut that down the middle, you get a 4:3 ratio, therefore the diagonal has to be 5, a squared. So 3 squared plus 4 squared equals 5 squared. So that's the first of your Pythagorean triplets. Again, in the Freemasons have this as an important symbol, part of, again, I think it's to get to the third degree. Very important person in regards to the development of Australia was Governor Lachlan Macquarie. He set up a lot of new towns. He redefined the street plans of many existing places, and for instance what they referred to as Macquarie towns, these 5 towns to the north west of Sydney, all set up by Macquarie. And there are 2, Windsor you could say is the capital, and it has the street plan, so each block is 8 chains by 12 chains, one chain being 66 feet, and all that other number stuff that comes in there from those measurements. But you could just shorten that down to a 3:2 ratio. So what you have is just a series of 3, 4, 5 squares. Now, Windsor is unique amongst the 5 of those Macquarie towns. All the other 4 share a same, their street blocks are all 5 chains by 12 chains. 5, 12, 13 is the second Pythagorean triplet. So Windsor has a 3, 4, 5 triangle, and all the other of those towns have the 5, 12, 13, the second of the Pythagorean triplets. And again, just one of these elements where Lachlan Macquarie, who was even described in his biography as a conscientious Freemason, and you can see by his the architecture and the way, not just his he had a very interesting social influence on Australia, essentially moved Australia away from the class system and developed a more egalitarian. But in his designs of his streets and the towns and stuff that he set up, it's all very by the numbers and by the geometry. So that's one example. Another one would be the Manitoba Legislative Building in Winnipeg. Frank Albo has studied this a lot. I've got some videos on my own as well. But the proportions of the building is 3:2, so 2 high and 3 wide, which again gives us the 3, 4, 5 triangle. And even for instance, the cornerstone ceremony was laid when Mercury and Venus were up above these astronomical connections. There's always multiple layers in these things. For instance, in the Parthenon, the length to width is 9 to 4, the height to width is 9 to 4. Such as Anne Balkins and J. Caprath, who have studied it, where we have these 2 to 3 ratios and 4 to 3 ratios built throughout very musical proportions. But even so, these same proportions in ancient architecture, well, you can even see like in the modern world. So, for instance, the old TV screens were 4 by 3, 3 by 4, 5. So you have your 3, 4, 5 triangle. Now, even that would, so a 4 by 3 television, well, now we've gone to 16 by 19, which is 4 squared by 3 squared. But these are how these very elemental vesica geometry is just so, well, everywhere to be found around the world, really. Ancient times as well. So, but again, Pythagorean Theorem, around about 500 BC, by, well, Pythagoras. And that's, again, no evidence, firstly no proofs and no direct evidence of Pythagoras, but writers shortly after have sort of mentioned it. But again, this thing, well, it can't be in the past, it must be Greeks. Well, if at same level demand for evidence was asked for, then the Greeks didn't have it up until 3rd century BC as well. So around about the time of Euclid. But how much older was this being put into practice? So again, we'll go back to, for instance, Stonehenge, 2,000 years before Pythagoras. And we have, even in Stonehenge phase 1, then we had Stonehenge phase 2, Stonehenge phase 3, and then to A and B, and then Stonehenge. So Stonehenge we see now is the final phase of it, but it began with a henge is the earthworks around that. So there are henges there, so that would be a henge in essence. But the stone part is separate. But Stonehenge developed, and then eventually come to the Stonehenge we know now. But the station rectangle has always been there, and that station rectangle is the second so the first Pythagorean triplet 3, 4, 5 triangle. The second Pythagorean triplet is 5, 12, 13. Now remember, all right angle triangles you can apply Pythagorean theorem, but a Pythagorean triplet is when it's an integer, a whole number. So 3, 4, 5, or 5, 12, 13, and we see that in the station rectangle. Richard Heath pointed out, so we have Stonehenge, Lundy Island, and the Presley Bluestone Quarry. So a lot of, not the giant stones, but the other bluestones which were there earlier and come from Presley, and that creates a 5, 12, 13 triangle as well. Also the distance of 108 royal miles by 45 royal miles, which is nice because that's 45 plus 108, 150. But anyway, the royal mile, but whether it's royal miles, mobile phones, however you measure it, the proportions are there, and I think it's one of these interesting things. Long scale alignments, because that's my bias, not really, but yeah, but these long range, they're very intriguing because it's you're asking a lot of coincidence in some of these things. But now, for instance, everyone knows Stonehenge, but there are hundreds of henges and hundreds of stone circles as well. But now, for instance, Woodhenge, and these have been studied by others as well. And he's sort of pointing out, so we have a 12, 35, 37. Okay, that's a Pythagorean triplet. 12, 35, 37. And he's pointing to this at Woodhenge. And so again, you have these, 3, 4, 5, 5, 12, 13, and these other Pythagorean triplets. Of all the sort of designs that they could have come to, it's interesting that they do come to those. And so Stonehenge, mentioned that. Now Alexander Thom went across, especially Western Europe, studying these places, and he was looking at proposed something called the Megalithic Yard. I have some older videos on that. I want to revisit that because there are a lot of lovely connections with that as well. But for instance, Karnak in France, where we have these giant stone alignments, but amongst there, so we have dolmen, monolith stone circles. For instance, it says stone circle, now it's partially underwater. And I've done some videos on like these are just all by these very interesting specific measures. But we have a Chrysono over Cromlech. There's the aerial view. One of these places surveyed by Alexander Thom. It brings us back to, well, the Vesica, which has a 3, 4, 5 triangle built into there. So that also has these proportion 3 to 4. So you could even say, you know, just the inherent proportions, but now the diagonal comes across there. And it's question is, did they really know? But well, the measurement, the proportions and measurements they chose are just repeated through to the modern age. And so let's look at the pyramids as well. So we have the Great Pyramid, Caffrey Pyramid, Menkaure Pyramid. Older videos recently post some compilations as well, looking at the very simple, lovely geometry that not only connects these pyramids but connects them to the others. But the Caffrey Pyramid, the one which still has the casing stones on the top, often confused for the Great Pyramid, but it has a proportion of 3 wide by 2 high, so 3 to 2 the Vesica as well. So it's essentially just made up of 2 right angle 3, 4, 5 triangles. So we see the Vesica 2 to 3. You can just post, that's the Caffrey plan, and therefore it has to be 2 of these 3, 4, 5 triangles. That same ratio, for instance, this is one example. The base of the Red Pyramid compared to the height of a Red Pyramid is 3 to 2. Again, I've gone through this quite extensively, and how, again, that these sort of ratios connect now. For instance, in the King's Chamber, amongst many other interesting mathematical geometric connections, we have a 3, 4, 5 triangle across the diagonal. And the Egyptian rope stretchers would use a rope with knots tied in it, so you have a 3, 4 and a 5 side. Now it's often, and again, no direct evidence of it being used in the very ancient part of Egypt, only up until the essentially the Ptolemaic Greek era. But again, given that this comes in so many different places now, again, a series I did unlocking the pyramids, looking at the Giza Plateau. Now, from this 0 point, what I'm proposing at the door to the Caffrey Valley Temple, which runs right up the Caffrey Causeway, Giulio Magli did some on this, and and then I extended it. Now, for instance, if you think there are 3 seasons in Egypt, each of 120 days. Egyptian New Year begins on the summer solstice. The sun will set directly in between the Caffrey and the Great Pyramid, and for the next 120 days the sun's going to keep moving south, south, south until the end of the flood season, Arquette, and that's 37 degrees. Now the precise number, right angle triangle 36.869, round that off to 36.9 or 89, but again, within the how you measure the solstice, you begin on the first day or the last day, well, you'll get a 36.87 degrees, just like the 3, 4, 5 triangle, which is, again, the defining angle of Caffrey's pyramid from the 3, 4, 5 Pythagorean triplet. And the King's Chamber now. So there we have Giza. Okay, let's go over the next one. So in this area up here, so where the canal, it's a bit obscure, but there's a canal that enters the Lake Moeris. Now I always forget that name. All of the great pyramids, the large pyramids, are north of that location and on the west side of the Nile. Now there are hundreds and hundreds of smaller pyramids, down into Nubia and elsewhere, but of the famous Egyptian Great Pyramid, so we begin here at the Giza Plateau, where we have the 3 most famous pyramids. You can even, 1, 2, and 3. And the Caffrey pyramid having the 3, 4, 5. But let's look at these others. They go down further south. They're all not only that same proportion as Caffrey, so 2, 3, 4, 5 triangles. They're also a standardized width and height. But the point is that this same geometry can be found in these pyramids. But what's more, it can be found on ground orientations down in Abydos and Thebes. Now we go to Thebes, so Valley of the Kings, Valley of the Queens, and we have like Luxor and Karnak Temple and some very important sites down there in Thebes. And so the Luxor Temple, notice there's an offset here, but the main temple axis is at 36.87 degrees. It's the same angle as Caffrey, and the same angle which defines the 120 days of the Arquette season. And the mortuary temple, Ramses III. Now the main axis points to the Valley of the Kings. I did this, so I'm just showing just a quick, I just want to focus on the 3, 4, 5 connection. So that points off, main axis points off to the Valley of the Kings. We have this courtyard here, which again is offset like Luxor. But in this case, the offset part, well, the angle is the 3, 4, 5 triangle angle as well. And many other interesting, again, connecting angles, but that's for that I've previously mentioned that. In Deir el-Medina, this was up in the hills above Thebes. That's where all the craftsmen lived and had their workshops that were working in the Valley of the Kings. They had their own, they were very well provisioned, had very high standard of living and special conditions under which they existed, and they were even rich enough to make their own pyramid tombs. Okay, but again, the temple, well, the angle is the same one, reflecting the Caffrey Pyramid, which has Arquettes and the flood connections. But we go up to Abydos, so the famous Osiron, which is behind the Temple of Seti. They're on the same alignment, and that alignment is 36.87 degrees, just like the 3, 4, 5 triangle of Caffrey. Now, Caffrey's pyramid, it has that equinox alignment. And now on the equinox pyramid of Kukulkan in Mexico, the stairs on the equinox, or is it? Yeah, sorry, I always get now, but on that solar event, the serpent appears. So you see the serpent's head, and it goes down the staircase. Now the staircase is a 45-degree angle, but these terraced steps of the main body of the pyramid, not the steps, but the pyramid itself, are angled at 53 degrees. So again, you can just superimpose the Caffrey Pyramid on the top, the 3, 4, 5 triangle, and it's also in there, plus the interesting astronomical connections. So of course, Pyramid of Kukulkan come quite later in terms of time, but it was there a long time before Euclid's Elements got to South America. And of course the pyramids and ancient sites in France and England having these Pythagorean triplets a long time before Pythagoras. And of course, well, they didn't have any, there's no proof, they didn't have a proof of it in a mathematical sense. You need a proof. Well, there's no existing proof of Pythagorean Theorem, yet we call it Pythagorean Theorem. So again, what's good for the goose is good for the gander, and then you see how often it appears. Now, at the very least, those proportions were very, very important to the Egyptians and to these other people as well, because you just see it repeated. Whether they understood the 3, 4, 5 triangle and Pythagorean Theorem, well, we can argue and discuss that, and then it's, again, without a smoking gun document. We don't really know, we never probably will, but at the very least it was significant enough for them to use this geometry, this very elemental geometry, in their designs. And again, these designs also all have astronomical alignments to solstice equinox, for instance, as well. However, long before Pythagoras, we come to ancient Mesopotamia and a clay tablet which is known as Plimpton 322 from around about the year 1700 BC, so 1200 years before Pythagoras. Daniel Mansfield and Norman Wildberger, here from the University of Sydney. And what they pointed out was by looking at this clay tablet. Now again, with these really ancient clay tablets, what you'll find is that there are inventories and business documents, even some of the oldest letters are business. It was more like, rather than inventing writing, to write down stories that had already been preserved through the oral tradition for a really long time. Just like in Egypt with this proto-hieroglyphs almost certainly being tax records, we find that these old writings have their lists, spreadsheets, and this type of thing, business contracts, and that was probably the driver of writing. But amongst astronomical observations that were recorded, Plimpton 332 contains Pythagorean triplets: the 3, 4, 5, the 5, 12, 13, so 3, 4, 5 triangle, 5, 12, 13, 7, 24, 25, 9, 40, and 41. And it was fascinating because they're talking about they were approaching trigonometry essentially in a different way, in a much more user-friendly way as well. But also amongst the ancient tablets, we have YBC 7289. And there's the image. Now these are from a great book if you're into Pythagorean Theorem, and both the non-controversial elements of it, but also the controversial elements of it. Hidden Harmonies by Robert and Ellen Kaplan. But this particular clay tablet, and well, it has writing on it, which they weren't using decimal points. They would write in fractions. You can even see 60, 3,600, 2,000, 216,000 because of a base 60 system. So 60 minutes per hour, 60 seconds per minute. So there are 3,600 seconds per hour. That also applies on the compass, 360 degrees. Each degree is made in 60 minutes, and each minute has 60 seconds. So 1 degree on the compass is 3,600. And these are also just those lovely harmonic numbers which are used even later with different numeration systems. But the point being that they calculated the square root of 2. So if you convert this fraction into a number, you get 1.141212962. And I think I've already got it up. Okay, now let's get this up. There's the square root of 2, 1.414213. So they've got the square root of 2 down to the, and if you round it off to the 4 to the 6th decimal place. And the whole thing with irrational numbers and the square root of 2 on one of the stories to get with Pythagoras murdering one of his, you could call it a rival. But again, we have this pointing to, that they might have done their maths different. They might not have written proofs now that we are required in modern times to do, but at the very least they were understanding the principle of it. And when you get to these higher level, so 3, 4, 5 triangle, one thing, 5, 12, 13, but when you're getting to triplets such as a 40, 41, and 9, well, that's showing an understanding that it's not just like a coincidence. Why is everyone before Greeks just deemed to be so clumsy and anyway. There's also now not the original surviving document. Now I won't butcher that pronunciation, but there was an actual proof, and This is one of the proofs of Pythagorean Theorem, and maybe as early as 1000 to 200 BC in China. So just about the time of Euclid's Elements at the very latest, or 800 years before at the earliest. Now these same proportions that relate to Pythagorean Theorem, which we also get from the Vesica Pisces, also applies to music theory. So Pythagorean music theory, but of course again the Greeks didn't invent music. This is an old thing, and the emblems of this are also very important. For instance, modern, so the Order of Druids, Freemasons, and others as well. Music was very important symbolically, but also in the real sense. Now we have the lyre, constellation, but I won't go into that. But again, we're seeing this really advanced, well, actually not really advanced, but it's much more advanced than what we would give credit for, and what is generally accepted. Again, there is a really strong bias that, before the Greeks there was nothing, but this ancient symbolism also. Speaking of the 3-4-5 triangle and how important it is in masonry, we have the compass and square. Now the square is a 45, 45, 90 degree triangle. So 90 degree, you can apply Pythagorean theorem. And if we define the edge as 1, because it's 45, 45, it's a isosceles equal triangle. Two legs are equal, therefore that has to be the square root of 2. And again, we see that square root of 2 going back, but how that will relate to music as well, we'll come to this, but it's just one of those really, really important things. That's okay. Now the Vesic, now for instance, a 3-4-5 triangle comes from the 3-4 rectangle, which emerges from the Vesica. 4-3 is a perfect fourth in music, and the 3-2 ratio, which the Vesica is the perfect fifth. So there's interesting connections with Pythagorean tuning, and again with the proportions of the Parthenon and all these things in there. How Pythagorean tuning works so lovely with those harmonic numbers, which you get the 3-2, 2-3, 2-3, 3-2, 2-3 ratio from C, G, D, A, E, and B. But that's one way to, again with the Vesica, just add a circle in the middle. You can make a square, and from that square you get the 45, the builder square, which so the square root of 2 being very important there. But I want to get into music now. Equal temperament, and we see the perfect fourth is a 4-3 ratio. The perfect fifth is a 2-3 ratio. But what's interesting is, again, shout out to Space Creator for making me aware of this again quite a while ago. A lot of stuff to revisit there. But the tritone. So we begin at the unison is 1, so you have all these proportions. And we get to the tritone, which was called the devil's tone. I think it was even banned by the church at a certain point. But 1.4142, and the square root of 2, 1.414213. So it's a nice series of connections. So again, even if you're just looking at Pythagorean Theorem, it's just all the same numbers and proportions and emblems just keep picking up in the modern esoteric, or going back to the 7 liberal arts of a quadrivium. Arithmetic, geometry, music, and astronomy. And again, these ancient texts as well, and so even before Euclid or before the clay tablet, we see this built into the architecture itself. Now, you don't go and build a giant pyramid or a temple or any large structure without some design. You need an architect, and you need a design, and you need organization to put it together. And especially in something like a pyramid, where it's a very simple shape, but you can, just like when you design a cathedral or a city hall, they put effort into thinking about what is the right width, what is the right height. how wide should the rooms be from height to width to length. These are one of the key things that architects do and have always done, because that's the language that they're writing in, and geometry and measurement is just essential to this. It just won't happen without it. But okay, 3, 4, 5 triangles in the modern Masonic architecture, in the traditions, in major public buildings with all these other elements such as the Hermetic constant. Again, just like with those harmonic numbers, even like those are TV screens. I did a series on harmonic numbers, did a compilation recently. Even things like 1080 HD, 720, 4, all those harmonic numbers in that harmonic chart are built into modern systems of design, but they're also in ancient systems of weights and measures, and in the architecture once again. Where books don't exist, we have these stone structures, and they're textbooks written in stone. These type of designs, like, they were engineered. They were, again, there's no library to tell us about who built the stone circles and the henges, but there is a library of the survey that's been done of these places, and again, we're just finding the same connections, astronomical alignments, the proportions, sacred units of measurement, which also bring us to pardon, very important harmonic numbers as well. So yeah, just across the world, this esoteric symbols relate to esoteric knowledge, such as the 3, 4, 5 triangles, and sacred geometry is nothing without the geometry. So you could even, geometry is sacred rather than sacred geometry. But again, just found in the architecture, also in the texts that do survive. And again, it's just pointing to this much more interesting story of history. And the Greeks didn't have supercomputers, but they were able to calculate these things. It's basically with an abacus and some logic, some reason, and why this can't be extended to people previous to them, such as all those pyramids and the layouts of the period of temples, such as the Osiron and Temple of Seti, or those multiple places in Thebes as well. It's just a bit mystifying to me, because it's just deemed to be fringe. Therefore, we must look at it kooky. But we have measurement and we have math, and that's at least the equivalent of much of the orthodox view of things, where again they just take a few pieces and use reason to create a pattern. Well, we're seeing a mathematical measurable pattern here as well, and because it's measurable, I would think that it carries at least as much weight as the conventional viewpoint, it is. But if you're interested in sacred geometry, you don't have to literally read Euclid's Elements, but I don't think you can analyze these things without a basis in geometry. To be blunt, and that's you literally need it. There's sacred geometry is just sacred without the geometry, and sacred is a fuzzy word that can mean anything to anyone. But geometry is geometry. The measurements are the measurements, and the proportions are the proportions. They're tangible. You can test them, and even the selection I've showed here is, again, it's only a small sample of that. It's the modern temple or the ancient temples have the same features, and it's just in a geometric, measurable, mathematical alignment sense in that as well. So that's it for this video. I hope you enjoyed. This was a series in the past, but I've re-narrated it, and I'll delete the older one because I was missing a few pieces, and there were one or two boo-boos there along the way. But again, hope you enjoyed. SJD. Have a good one.